In this video, we're going to continue talking about the concepts of chapter 7. Now we're going to focus on gases. Gases have limited attractive forces. And whenever we talk about gases and their behavior, it is important to discuss the kinetic molecular theory. This molecular theory basically defines how particles of gases behave. At the core of the theory, what we're understanding is what gases consist of. Gases are going to consist of small particles that move rapidly in straight lines. They have essentially no attractive or repulsive forces. They are very far apart. They have a volume that's smaller compared to the container where they're occupying. And lastly, they have kinetic energies that increase when temperature increases. As you can see in the image on the right, this container is going to have some gas particles. And these gas particles, which are illustrated with these green balls and orange balls, the way that they move within the container, as you can see, is in a straight line by the shadow that they're marking or it has been utilized in this image. Now, whenever these particles meet another gas particle within the container or the walls of the container, we can actually observe how they are going to move continuously within the space that they're occupying, but always in a straight line. Whenever we talk about gases, we must discuss them in terms of their four properties. And that's because there are four properties that are going to be utilized in order to describe gases in general. The first property that we have is called pressure. And pressure is defined as the force exerted by a gas against the walls of the container. Pressure, it is abbreviated with, with a capital P. And when it comes to the units of measurement for pressure, we can see that we can utilize the measurement of ATM, millimeters of mercury, torr, or Pascal. Those are all different units of measurements that can be used for pressure. The second property that can be utilized in order to describe gases is volume. And volume is defined as the space occupied by a gas. The units of measurements that can be utilized in order to measure volume include liters and milliliters. Next, we have temperature. And temperature is going to describe specifically how the rate and the kinetic energy for the motion of these gas particles are going to be changing. In previous chapters, we actually discussed the definition for temperature, which is the measurement that defines how cold or hot a particular substance is. We're going to observe that at times when it comes to gases, we can utilize the units of measurement Celsius or Kelvin, but specifically Kelvin is required if we're doing calculations when temperature is present in our equation. The last property that we need to take into consideration for a gas is going to be the amount of gas. And the amount of gas is going to be defined as the quantity of gas that is present in the container. When it comes to the units of measurements, we can see that this gas particles can be measured in grams, but when it comes to calculations, specifically, the number of moles is what's utilized when it comes to calculations. So now that we know what are the four properties that describe that can describe a gas, we are now going to focus on the behavior of gases by discussing gas laws. So what is a gas law? A gas law is going to be a specific definition that has specific parameters that is going to describe the behavior of a gas. And the first gas law that we're going to be studying is Boyle's law. Boyle's law is going to specifically talk about the relationship between the pressure of a gas versus the volume of a gas. Whenever we're looking at the relationship of pressure and volume, let's understand that the other two properties, meaning temperature and amount of a gas, need to be held constant. So then we can see the variation between pressure and volume. Now, Boyle's law states that the pressure of a gas is inversely related to its volume because the other two properties are held constant. So what this means is that we can actually write it as pressure is proportional. So that symbol is proportional to 1 over V. So when we look at the relationship between pressure and volume, and the three lines do not mean equal, they're going to mean related to. What happens overall is that if in a system the pressure of a gas increases, the volume is going to decrease. And vice versa. In a system where pressure specifically goes down, the volume is going to go up. Gas laws have a particular equation that can be utilized in order to do calculations. And we can observe that specifically for Boyle's law, the equation for this gas law is the following. P1 times V1 equals P2 times V2. What this means is that the symbols that are defined by the number 1, those are going to be initial conditions. And then the symbols that are given by the number 2s are going to be final conditions. One of the interesting things is that Boyle's law actually explains something that we must do in everyday life in order for us to live, and that is breathing. Here we have some images that are illustrating how Boyle's law is actually related to breathing. Every time we inhale air, one of the things is that our rib cage expands, because when we are inhaling, what we're doing is that we are increasing the volume of that gas, that air gas that is entering our body. And in turn, what happens is that the lungs are going to decrease the pressure that they sustain in order for the lungs to get inflated. Now, whenever we are exhaling, we have to increase the pressure that it is in the lungs. And then in turn, what's going to happen is that we're going to decrease the volume of that air inside of the lungs. Let's now see how we can actually utilize this concept of Boyle's law, but in a chemistry problem. Let's do the following example. This problem states Freon 12. In Freon, the chemical formula for it is CCl2F2. It is a gas that is used in refrigeration systems. The question read, what is the new volume of an 8.0 liter sample of Freon gas initially at 550 millimeters of mercury after its pressure changed to 2,200 millimeters of mercury at constant pressure and number of moles? Whenever we're trying to solve these problems, we must state the information that it is given. So in this problem, we are given the initial volume, which is 8.0 liters. We're given the initial pressure, which is 550 millimeters of mercury. And then we can see that the pressure changed. So in the change, that would be P2, our pressure went up to 2,200 millimeters of mercury. So according to this problem, we need to actually figure out what is the new volume. So what we're calculating is V2. So first we write, so you can see all the information given. Then we proceed to write the equation that we need for Boyle's law, which is P1 times V1 equals P2 times V2. Utilizing algebra, we can actually separate by itself the V2 term because we can divide on the right side of our equation, and on the left side of the equation, we can divide both sides by P2. So when using algebra to actually separate the V2 term by itself, we notice that this equation can be written as V2 equals P1 times V1, everything divided by P2. Even before we start the problem, we can actually rationalize what is going to be relatively that number that we are going to be obtaining. If we use critical thinking and we know the trend that Boyle's law actually shows for pressure and volume, we can remember that when it comes to pressure in its relation to volume, if one goes up, the other one goes down, and vice versa. We can see that from P1 to P2, our pressure goes up. So what that's going to do to the volume is that it's going to decrease. So most likely we can already estimate that that V2 is going to be around it's going to be less than 8.0 liters. Because since I know that the volume is going to go down, the value of V2 is going to be less than 8.0 liters. Let's plug in the numbers into our equation. So P1 is 550 millimeters of mercury. V1 is 8.0 liters. We're going to divide everything by 2,200 millimeters of mercury. Millimeters of mercury cancel. And our answer will be in liters because it's the only unit that is standing during this process. So now let's take a moment and plug this into the calculator. 550 times 8.0 divided by 2,200 gives you a calculator display of 2. But because each one of the measurements that we have here has 2 significant figures, the final answer here is going to be 2.0 liters. And from our analysis in the beginning, we can observe that this number makes sense because 2.0 liters is actually less than 8.0. So this is the correct answer. Let's now move on to discuss another gas law when it comes to the behavior of gases. The next gas law that we are going to be studying is going to be Charles' law. Charles' law specifically looks at the relationship between temperature and volume. When we are doing Charles' law, it's important to note that we're looking at that temperature of a gas in terms of Kelvin units. The reason why we do Kelvin units is because even if the temperature of our gas is really, really low, upon conversion to Kelvin, understand that most Kelvin unit values are going to be still positive, so we don't have to handle a lot of negative numbers. So that's one of the reasons which at times is a little bit more favorable. But this is just giving you at least an insight into the values that we obtain mostly when we are doing these equations. Since in Charles' law, we're looking at the relationship between temperature and volume, that means that the number of moles for a gas is held constant along with the pressure. For Charles' law, this is our equation. Initial volume divided by initial temperature equals final volume divided by final temperature. According to the law, when we look at the relationship between volume in relationship to temperature, if one goes up, the other one goes up. In the same manner, if one of these two properties goes down, the other one goes down. Now, let's do a practice problem to understand in more detail Charles' law. When it comes to Charles' law, we have the following problem. It states a balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon at constant pressure and number of moles? Let's first write down the numbers or measurements, in other words, that have been given to us in this problem. So when we look at this, we can see that we are given the initial volume, which is 785 milliliters. We have the initial temperature, which is 21 degrees Celsius. And we have the final temperature, so T2, which is 0 degrees Celsius. And here, what we need to actually find is going to be V2, the new volume. So now that we wrote all the information given, because our temperature is given in Celsius, the first thing that we have to do is change those units of temperature all the way to Kelvin. You may remember that whenever we're changing to Kelvin, temperature in Kelvin units equals temperature in Celsius units plus 273.15. So what that means is that if we look at T1, if we do 21 plus 273.15, that means that this temperature in Kelvin is going to be 294.15 Kelvin. And when it comes to T2, this is going to be 273.15 Kelvin. Now that we have converted our temperature into Kelvin units, now we can utilize our equation to find our V2. Similar to what we did in the previous problem, we can actually rationalize what's going to happen to our volume. In this case, when we look at the relationship between volume in relationship to temperature, we see overall that the temperature went down. And since in Charles' law, as temperature goes down, volume goes down, we can already expect that that volume is going to be lower than 785 milliliters. Let's demonstrate it by looking at the correct answer. My equation is V1 over T1 equals V2 over T2. In order to separate the V2 term by itself, all I have to do is multiply both sides by T2. So when I rearrange this equation, and this is my symbol for rearranging, I'm going to state that V2 equals V1 times T2, everything divided by T1. Now let's plug in our numbers. 785 milliliters times 273.15 Kelvin, everything divided by 294.15 Kelvin. My Kelvin units cancel. So when I look at my final answer, because the unit for volume is in milliliters, this answer is in milliliters. So we're going to take 785 times 273.15 divided by 294.15, and we can observe that the result of this is going to be 729, so 729 milliliters. So when we are trying to determine the number of sig figs that we need in our final answer, please note that specifically for Charles' law, you're going to look at volume given and the temperatures after their conversion. Because in this process, we're multiplying and dividing. Overall, even though volume 1 has 3 sig figs, temperature 1 has 5, and temperature 2 has 5, it's important to note that overall we need to round to 3 sig figs. That's why our final answer is 729 milliliters.